Hello everyone, my name is Shadeep and I'm an instructor for today's course. As usual, we'll try to do some review on FE chapters. And today's topic that we are going to focus on is also electronics. In the last video, we kind of talked through about the different types of PN junctions and we tried to realize about some of the equations we can use to measure the capacitance, to measure the voltage. But today's class, we would focus mostly about BJTs, MOSFETs, and diodes. We'll try to review some of the questions and equations that comes in your FE exam in electrical and computer engineering. We'll try to understand the concepts. We will try to understand the equations. And then at the end of the review, we'll try to see how those equations can be applied to the questions that come in our FE exam. So without wasting any further time, let's start on with the class. So let me start sharing my screen. So as I said earlier, what we would try to do today, we'll try to go through diodes first. So let me start with the basic equations over here. Let me just take a snipping tool and take a snapshot of this one. And go on explaining this one. Now, as for those of us who are not familiar with the concept of diodes, what diode does, it helps in rectification. And if you're wondering what rectification is, so supposedly I have an AC signal. And since it oscillates between a positive and a negative, and it's an AC signal. A diode would be able to convert it to a DC signal, making sure that it only conducts in the positive end of the input cycle. So this is the input cycle, and this is our output cycle. So a diode is ensuring that it only conducts in the forward bias. We call it the forward bias direction, making sure that only it conducts in the positive end of the cycle, and the negative end, it does not conduct. And then again, it conducts in the positive end, and in the negative end, it does not conduct. Again, it conducts in the positive end only, and again, it does not conduct. So in a way, it just ensures that it only conducts in one direction, that's in the forward bias direction. If you're trying to visualize it, it's like this. You have a diode. You have an AC signal. And you have an output across this one. So this is your output. And this is the signal that you're getting over here. And this is the AC input, and this was the signal that you were applying. Okay. So if you're trying to measure how much current, now you can see in this case, it's a series circuit, right? Because it's just connected across in one nodes, right? If you're trying to measure exactly how much current is actually flowing through this diode, or in this circuit in this case, because it's a series circuit, a graph would usually look like this, where you can see from the graph that it does not conduct until and unless you apply at least a minimum voltage of 0.5 to 0.7. What I mean by that, that means unless my value of input reaches at least a 0.5, or in certain cases 0.7, it would not conduct. I hope I'm making sense on this one. Now, once I applied that minimum threshold as the input to the circuit, it will start conducting. And if you're trying to measure how much current is flowing through this one, it can be determined using the Shockley's equation over here, where IS is the saturation current, and as you can see, this one is the emission coefficient is given over here, and it's typical. We are mostly considering silicon in most of the cases. So unless it's had some other element, uh, in those cases, they would give you it's a constant. So you would try to use that coefficient, but if not, you can use a 1 for silicon. And I'm pretty sure if you watched the previous video, we discussed about the thermal voltage, and it was given in the previous equation. If you're trying to review the notes, like over here, you would find the value was given around 0.026 volt at room temperature. So this VT is a constant which is approximately 0.026 volt. Okay, so unless you're changing the temperature, you would use this value. However, if you are given a different temperature, which is very unlikely in this cases, you would plug in the value over here and figure out VT. And if you're wondering what KT is, it's given over here. It's 1.38 into 10 to the minus 23, and Q is the charge of a single electron, which is always 1.6 into 10 to the minus 19. So once we plug it over here, we will be able to figure out how much current is flowing through this diode. Okay. Uh, okay, so we are done with the basic diode over here. Always remember in the forward bias, if it was a DC circuit, this is called, this is an anode and this is a cathode. Anode is in the negative end, cathode is in the positive end. Okay, so the cathode always has to be connected to the positive end of the cycle, and the anode is always connected to the negative end of the cycle. And this is a resistor or a load, whatever you prefer to call it. Now, this is how the connection should be. Now, a Zener diode is also a diode, as the name suggests, but the difference over here is in terms of symbol, it is represented by this, but it also helps you act as a voltage stabilizer. What do I mean by that? That means if a Zener diode is rated 4 volt, it would help you to hold on to that 4 load. If it's applied across the load. What do I mean by that? It's supposed to have a circuit, and I want the voltage across that load to be uh, like 4 volts. So this Zener diode supposedly is labeled as 4 volts. Now I'm trying to make sure that the voltage across this load RL is 4 volt as well. So all I have to do is connect a Zener diode in parallel with this load. Once I do that, it would help you hold on to that 4 volt rating. So a Zener diode is very similar to, as you can see, it functions very similar to a basic diode in terms of a current graph. But the advantage that it gets over here is that it can be used as a voltage stabilizer because it helps you to hold on to that particular voltage. In this case, it's helping you hold on to that 4 volt if it's rated 4 volt. I hope I made some sense over here. So those are the only two equations you would be needing in terms of diode. But let's move on to the next equation about BJTs. And once we focus on BJTs, we'll try to solve some equations with diodes and BJTs. So now let's move on to the next equation. Now, a BJT, for those of us who don't know, is a transistor which is used basically in two ways. One, it can be used in amplification. So let me write it down. It can be used in amplification. A, or it can be used basically in switching. So if you're wondering how is it used in amplification, it's very simple. Uh, the gain, so it is a current amplification. So BJT is basically a current amplification. And you can see over in this equation itself, over here. So a BJT, as you can see over here, this is the base, this is the emitter, and this is the collector. Your input is applied to the base, and we are usually collecting an output from the collector or the emitter. So in most cases, the collector. And you would find that your collector current is more or less, I'm not saying exactly, but it's more or less equal to my emitter current. Because my base current is usually very small. Okay, so given that, so my input is my base and my output is usually my collector. And if you're trying to figure out how much time it is helping in amplification, it is given by this coefficient beta. So if I say my beta is 100, that means if I'm giving an input current of 1 milliampere, my output current when collected through IC, my collector, would be magnified by 100 times. So it would become 100 milliamperes. If now beta is an inherent property. We cannot change it. It is affected by a lot of factors like doping and all that. So you cannot do anything about it. It comes to you with the rating. So you probably have to just go through it, like the value that is given to you, and you have to plug it over here, and you would be able to figure out how much is your collective current. I hope I'm making sense over here. So you basically don't have to know a lot of these. Okay. But let me just go through the equation, the ones that you basically need to know. So you basically need to know this one. The first one is this one, which I just discussed. So IB is your input base current. When you're multiplying it with the beta, which would be given to you, you would be able to calculate the collector current. Now, collector is given, as I said, collector is approximately equal to emitter current, but it's not exactly equal to, but it is given by a constant alpha. Okay, now if you're wondering how much alpha is nothing but beta divided by beta plus 1. So you would see beta divided by beta by 1. Right? So beta, as I said, is usually like it could be 100, right? So if you divide it 100 by 100 on 1, now I can just do the calculation on the top of my head and I could say it's almost equal to 1, right? So 100 divided by 101 is almost like 0.99. So that is the reason why I said when you multiply 0.99 with your IE, you're getting IC. So that's why I said, since it's almost 0.99, so I can approximate it as almost equal. So IC is almost equal to IE, but if not exactly equal, it is given by this constant alpha. And how do we find alpha? Alpha is given as beta divided by beta plus 1. And then emitter current is nothing but the summation of your collector current and your base current. Let me just erase this one so that you could just visualize it very clearly. Okay, now let me just zoom in a little bit so that you guys could see it. Now, the next thing that you basically trying to understand is collect. So collector current is also given by this equation. Uh, IS is the saturation current. Now the thing is like it would operate uh, it can operate in three regions. One is the cutoff region, and basically we will be focusing more on the saturation region right now. Active region and saturation region. We won't focus. So the saturation current is in this region. So when the emitter saturation current, so we would use this IS is when it's operating in the saturation region. When it's operating in the saturation region, that particular emitter current, we would choose that. That is the emitter saturation current. Base to emitter voltage, it's working like a diode, so you can assume this voltage is always 0.7 if it's not given. So VBE, if it's not given to you, you can assume it's a 0.7. Okay, so you know your VBE. VT is the terminal voltage which we just discussed. I just showed you. It was, I think it was 0.026 volt, but let me just cross check. Yeah, 0.026 volt. So your VT is 0.026, your VB is 0.7, and this is like exponent which you would use in your calculator. So you will just plug in the exponent and give this ratio, whatever you get. So this is a constant value you can more or less say. And IS is saturation current. So yeah, it would be given to you. Now, so you basically have to know this couple of equations, not many. But what you need to know over here, now coming over here. So what happens is a diode can operate in three regions. One of the region is the cutoff region. It is in this region where it would work like an open circuit. As I said, it works as a switch, right? So when I say it's a switch, when it's not like when it's an open circuit, that's in the cutoff region. Usually, it would be when you're not supplying enough base to emitter voltage. As I said, you need to apply at least a 0.7 threshold voltage for it to work. If you're not applying that at least 0.7 volt between base and emitter, it would not conduct. So in that case, it's operating in your cut-off region. Okay. Saturation region, as I said, it's in switch, it's in two regions, either on or it's an off. So when it's in the off cutoff region, it's an open circuit. When it's in the saturation region, BBE saturation, BCE saturation. So this would be in the saturation region. And when it's in the active region, uh, it's basically working like an resistor or an amplifier, right? So depending on your beta, IB, so depending on how much this you would be has better emitter forward bias, base collector junction reverse bias. So in this case, it's working basically in the active region. So if I'm trying to visualize it, let me get a Word document. So in the cutoff region, it's an open circuit. And the saturation region is like a short circuit between collector and emitter. But if you're wondering about what do you think would be in the active region, it's almost like a resistor. Okay, so between collector and emitter, it's like this, a resistor. Okay, so I think that is, yeah, the thing here. Yeah, okay, so that's the saturation region, that's your active region, and that's your cutoff region. Now, moving on to, so this is when you're applying just a DC signal. As you can see over here, let me just enlarge it. These are basically when it is in a DC signal. Okay, so all these things that we discussed is for a DC signal. However, when it comes to an AC signal, which is a small signal analysis, there's more to it. So we won't focus on the small signal analysis in today's class, which we would keep it for tomorrow's class or the next class. But so we'll try to do some review questions based on this ones. Okay, so how about, let me stop sharing my screen and let me build up some review questions. So these are the two questions that I have apparently with me related to diodes. And as usual, I'll give you a 5-minute timeline. And within that timeline, you could try solving it. And after that, so I'll just keep this question over here. So if you're watching this video, you can practice it in real time in 5 minutes. And after 5 minutes, we will try to see uh, what's the solution of this too. Now, let's try to discuss the solution for this one. Let's zoom out a little bit. So the question was, how much is the current in this case, right? So assuming, like in this case, we had a diode over here, right? So if it's a diode, obviously, as we said, as we discussed earlier, if it's a diode, it's exact 0.7 volt. Okay, so in this cases, there are three potential drops. One is 10, one is 8, and one is a 0.7. So the potential difference, we know V equals to IR, and it's a series circuit, right? So we subtract the 10 volt, we subtract the 8 volt because there's a potential difference occurring between this, and there's also a 0.7 voltage drop because of the diode, because it's not said it's ideal. If it was ideal, this would have been 0 volt. But as if it's not mentioned as ideal, if it's on, you have to assume the voltage drop is 0.7. So the summation of the potential difference divided by the resistance would give you the current. I hope I'm making sense over here. Okay, the next question was, let's go to the question. So in the next question, basically, let me just Okay, so so in this question, what we basically tried to do was let's assume this one. So how about this? Let me stop the video for a minute. Okay, so let's share the screen again. So our question was this one. Calculate the no, not this one. It was this one. Find diode currents in the following cases. So what we have over here, so they're basically trying to figure out how much current is in D1 and in D2. So the solution is given like this. Let us first assume that D1 and D2 are both on. As we know, if both of them are turned on, this is a 0.7 voltage drop. This is another 0.7 voltage drop, right? So you have to subtract the potential difference, 10 minus 0.7, because there's a potential difference. And then 5 minus a 0.7, and that is flowing through this 2K. So let me just show it over here. So there are two junctions. If you're trying to figure out how much current is flowing through this one across the 2K, you have to subtract the potential difference at one end from the potential difference at the other end. And you're dividing it by the resistance and you're getting the current. Okay. Now, the other way we could do is we can assume this one is off and only D2 is on. Okay. So when you're doing that, it's 10 minus 0.7 since it's on. And over here, since you don't have this, so you have to take this one. So this one's not working. So this is a minus 3 volt. So what you're doing is you're subtracting this. You're just focusing on this one. Okay, now you're focusing because this one is not working, right? So you do not have to focus on this end, just focus on this end. So 10 minus 0.7, subtract it from 3, divide by 5, and that would give you the current across this one. Okay, that's how you calculate the current. Okay, and yeah, so that's how you basically figure out the current. And now just to make sure. Yeah, yeah, I think so. We kind of did it correctly. Yeah. And the answer was B, by the way. So in case you're wondering, the answer was B. And this is how you basically, and it does make sense to somewhat level. Okay. Okay, so I think like let's keep it until here today. And in the next class, we can go through some questions on BJTs and finish the small signal analysis, that is the AC analysis of BJTs. I hope you enjoyed and learned something from this class. And yeah, have a great day.